Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The presentation of William Kingdon Clifford's abstract on the space theory of matter to the Cambridge Philosophical Society 1870, with its subsequent publication in their proceedings in 1874, marks a moment of extraordinary intellectual foresight in the history of physical thought. This document, barely exceeding 500 words, offers a conceptual blueprint for a physics that would take another 4 decades to acquire its mathematical formalization. To the modern reader, its propositions appear uncannily prescient, a preliminary sketch of Albert Einstein's general theory of relativity. An analysis of this work demands more than a simple acknowledgement of its prophetic quality. It requires a deep and systematic evaluation of the claims as Clifford himself laid them out, examining the internal logic, the philosophical underpinnings, and the sheer audacity of his assertions within the scientific milieu of the Victorian era. This essay will undertake such a critical evaluation, proceeding through the logical sections of Clifford's argument to assess the specific claims he makes about the fundamental nature of reality. The objective is to understand the work on its own terms, appreciating it as a self-contained, revolutionary prolegomena to a future physics, built upon a foundation of pure reason and geometric intuition. Section 1. The foundational hypothesis of variable space curvature. Clifford initiates his argument by directly invoking the work of Bernhard Riemann, specifically his 1854 habilitation lecture on the hypotheses which lie at the basis of geometry. The initial claim Clifford evaluates and accepts is Riemann's radical proposition that the metric properties of space, its very geometric character, are contingent upon physical phenomena rather than being fixed a priori truths. Clifford's first intellectual move is to elevate Riemann's mathematical possibility into a physical assertion. He posits that space itself is subject to variations in its curvature from one point to another. The specific language he employs, that we might find the curvature of space is variable, is a direct translation of a mathematical concept into a statement of physical reality. The critical evaluation of this claim hinges on its profound departure from the prevailing Kantian and Newtonian conceptions of space. For Isaac Newton, space was an absolute, immutable, and Euclidean container for physical events. For Immanuel Kant, Euclidean geometry was a synthetic a priori intuition, a necessary condition for any possible experience. Clifford's proposition dismantles both frameworks. By asserting the variability of curvature, he transforms space from a passive background stage into an active participant in the universe's dynamics. The evidence he offers for this claim is purely intellectual, a logical extension of Riemann's mathematics. He provides no empirical data, an omission that renders his theory a philosophical speculation in the eyes of his contemporaries. The strength of the claim, however, resides in its logical power. If geometry is the study of spatial relations, and if these relations are determined by physical bodies and forces as Riemann suggested, then it follows that a universe with a heterogeneous distribution of matter and energy must exhibit a heterogeneous geometry. Clifford's genius here lies in his full acceptance of this consequence, proposing that the familiar three-dimensional space of our experience could possess an intrinsic, albeit unperceived, and variable curvature, a fourth-dimensional warping understandable only through the lens of non-Euclidean geometry. His evaluation of Riemann's work is therefore one of complete adoption and physicalization, taking a set of abstract, mathematical tools and declaring them to be the literal substance of the cosmos. This foundational step is the necessary prerequisite for all subsequent claims in his theory. Section 2. The ontological identification of matter with geometry. Having established the principle of variable spatial curvature, Clifford presents his central and most revolutionary thesis. He claims that small portions of space are in fact of a nature analogous to little hills on a surface. This powerful analogy contains the core of his space theory of matter. The evaluation of this claim requires unpacking its dense implications. First, it proposes an ontological reduction. Matter is nothing other than a feature of geometry. The dualism between space as a container and matter as its content is completely dissolved. A particle of matter, in Clifford's view, is a localized region where space is intensely curved. The hill metaphor is particularly insightful. It suggests a region of positive curvature, a bump or protuberance in the fabric of space itself. This is a claim of identity, an assertion that the phenomenon we perceive and label as matter is, in its fundamental essence, a geometric property. The methodology here is again one of philosophical reasoning and analogical extension. He is building a model of the world based on conceptual parsimony. By identifying matter with curvature, he eliminates the need to postulate matter as a separate, fundamental substance. The universe, in this view, is made of one thing, space. Everything else, all the richness and complexity of the physical world, arises from the intricate and dynamic geometry of this single substrate. Critically assessing this proposition from the standpoint of 19th century physics reveals its astonishing ambition. The dominant model of matter was the atom, conceived as a tiny, hard, billiard ball-like entity, whose interactions were governed by forces like gravity and electromagnetism. Clifford's proposal replaces this entire mechanical and substantialist picture with a purely geometric one. The explanatory power of his claim, at this stage, is entirely conceptual. It offers a potential unification of the fundamental constituents of reality, a goal that has driven theoretical physics for centuries. The weakness, of course, is its complete lack of a mathematical mechanism. He provides no equations to describe how this curvature behaves or how it gives rise to the observed properties of matter, such as mass or charge. The claim is a qualitative hypothesis, a statement of what is without a full quantitative explanation of how it works, yet its intellectual elegance and unifying potential make it a profoundly compelling piece of physical reasoning. Section 3. A kinematic theory of propagating curvature. The third major claim in Clifford's abstract addresses the phenomenon of motion. Having defined what matter is, he proceeds to define what it means for matter to move. He states that this variation of the curvature of space is what really happens in that phenomenon which we call the motion of matter. This is a direct consequence of his ontological identification of matter with curvature. If a particle is a hill in space, then the movement of that particle from one location to another must be the propagation of this hill, the transference of the localized region of high curvature across the spatial manifold. The evaluation of this kinematic claim reveals a radical reconceptualization of causality. In the Newtonian framework, an object moves because a force acts upon it. The force is the cause, the motion is the effect. In Clifford's framework, the very phenomenon of motion is a continuous process of geometric deformation. There is no external force pushing the hill along. The hill's movement is an intrinsic, wayward propagation of a geometric state. This idea prefigures the concept of a field, where a disturbance in a medium propagates according to inherent rules. Here, the medium is space itself, and the disturbance is curvature. A critical assessment of this argument must acknowledge its internal coherence. It follows logically from his previous premise. If matter and space are one, then the dynamics of matter must be the dynamics of space. The motion of an object is revealed to be an illusion. In a sense, the object itself does not persist as a singular entity that travels through a static background. Instead, a geometric property, which we identify as the object, is continuously recreated at adjacent points in space, much like a wave travelling across the surface of water. The water molecules themselves only move up and down, while the wave form travels horizontally. Analogously, in Clifford's theory, the stuff of space reconfigures itself locally to produce the appearance of a travelling object. This claim, like the others, lacks a mathematical engine. Clifford alludes to the possibility that this propagation might be governed by laws, suggesting that a certain state of strain in the space might be passed on from one portion to the next. This hints at the idea of a differential equation governing the evolution of the geometry, the very concept that lies at the heart of Einstein's field equations. Clifford's claim about motion is therefore a profound insight into the nature of physical law, recasting it from a set of rules for interacting particles to a set of rules governing the evolution of the geometry of the universe itself. Section 4. The empirical objection and the postulate of local flatness. Clifford demonstrates a keen awareness of the primary objection to his theory, the profound discrepancy between his model of a curved, lumpy space and our everyday experience of a flat, Euclidean world. He anticipates the question of why, if his theory is correct, we are unable to perceive this intrinsic curvature. His answer constitutes the fourth major claim of his work, that the variations in curvature are simply too small to be detected by our senses or our instruments. He argues that the average curvature of the space we inhabit may be effectively zero, and that the little hills which constitute matter are of a scale so minute that their geometric effects are imperceptible on a macroscopic level. This is the argument of local flatness. The evaluation of this claim is crucial for the viability of his entire program. Without it, the theory is immediately falsified by common experience. The claim is a powerful and astute defense, and it introduces the critical concept of scale into physics. It suggests that the laws and properties of the universe may be radically different at different orders of magnitude. The geometric richness of reality is hidden from us because our existence is confined to a region of spacetime that is, for all practical purposes, flat. This is precisely the same reasoning that allows general relativity to coexist with Newtonian mechanics in regions of low gravity and low velocity, the complex equations of Einstein's theory reduced to the simpler formalism of Newton's laws. Clifford's argument is an intuitive, qualitative version of the same principle of correspondence. He further attempts to bolster his theory by connecting it to the pervasive concept of the luminiferous ether. He speculates this bending of space might be the very phenomenon that physicists were trying to describe with their mechanical models of the ether. This particular claim is less a core tenet of his theory, and more an attempt to build a breach to the contemporary physics of his day. Evaluating this move, one sees a brilliant strategist at work. He is attempting to solve one of the great problems of 19th century physics, the nature of light propagation, by subsuming the mysterious ether into his own, more fundamental, geometric framework. He suggests that the strain in space he mentioned earlier could be the very medium required for electromagnetic waves, while this specific connection to the ether would ultimately prove to be a conceptual dead end. It demonstrates his effort to make his abstract theory relevant to the concrete problems that occupied his peers. The core claim of local flatness, however, remains his most robust defense, a scientifically sound and ultimately prophetic argument for why fundamentally non-Euclidean universe and appear Euclidean to its inhabitants. Section 5. The cosmological and metaphysical implications. In the final sentences of his abstract, Clifford ventures beyond the realm of physics into cosmology and metaphysics, making his last and most speculative set of claims. He muses on the possibility that the universe as a whole might be a closed system, analogous to a finite, unbounded surface like a sphere. He suggests that, just as a finite number of hills can exist on the spherical surface, the universe might contain a finite amount of matter within a finite, yet edgeless, geometry. This claim extends his space theory from the microscopic scale of particles to the macroscopic scale of the entire cosmos. Evaluating this proposition reveals Clifford as a pioneer of modern physical cosmology. The idea of a finite but unbounded universe, governed by a non-Euclidean geometry, is a cornerstone of relativistic cosmology. Clifford, working decades before the necessary observational evidence or mathematical tools were available, arrived at this possibility through the sheer force of his theory's internal logic. If space has intrinsic curvature, then it is perfectly plausible that it could curve back on itself, creating a closed system. This would resolve the ancient paradoxes associated with an infinite universe. His final claim delves even deeper, touching upon the relationship between the physical world and the mind. He speculates that the laws governing the geometry of space might be connected to the laws governing the relationship between mind and matter, a hint at a profound psychophysical parallelism or a form of neutral monism. This claim is, of course, entirely philosophical. It cannot be evaluated on physical grounds. What it does, however, is reveal the ultimate ambition of Clifford's project. He sought a true theory of everything, a single, coherent framework that could account for matter, motion, the structure of the cosmos, and perhaps even consciousness itself. This final flourish is a testament to the intellectual spirit of the Victorian era, where the boundaries between physics, mathematics, and philosophy were far more permeable than they are today. The evaluation of this ultimate claim must be one of appreciation for its intellectual scope. Clifford is not merely proposing a new theory of gravity, he is sketching a complete worldview, a monistic vision in which all of reality emerges from the singular, dynamic substance of geometrics. In conclusion, a meticulous evaluation of the internal claims of William Kingdon Clifford's on the space theory of matter reveals a work of astonishing intellectual power and coherence. It is more than a lucky guess, it is a rigorously reasoned, if qualitatively expressed, physical program. The claim that space possesses a variable physical curvature provides the foundation. The subsequent claim that matter is an ontological manifestation of this curvature offers a radical principle of unification. The kinetic claim that motion is the propagation of this curvature provides a new theory of dynamics and causality. The defensive claim of local flatness provides a crucial bridge between the theory's predictions and empirical observation. Finally, the cosmological and metaphysical claims demonstrate the ultimate, holistic scope of his vision. While the work lacked the quantitative formalism that would define a complete physical theory, its sequence of propositions forms a logically sound and conceptually elegant argument. Clifford's method was one of analogical reasoning and the courageous pursuit of an idea to its furthest logical conclusions. He took the mathematical possibilities opened by Riemann and asserted their physical reality, constructing a vision of the universe that was internally consistent, explanatorily powerful, and, as history would demonstrate, profoundly accurate in its fundamental insights. The 1874 paper stands as a monument to the power of pure thought to discern the deep structure of the physical world, a set of claims that collectively form one of the most remarkable prefigurations of a scientific revolution ever committed to print.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.